Solutions and colligative properties. So basically, exactly what is a solution? Suppose if I take a beaker, I am taking water in this beaker. So this is water, and to this water I am adding sugar. That means before we add sugar to the water, we can identify the sugar particles. The moment we add sugar to water and mix thoroughly. So once we add sugar to the water and on mixing thoroughly, so we cannot identify the sugar molecules in the resultant solution, nothing but aqueous solution or resultant mixture. So here when we add sugar to water, we can observe that the resultant mixture looks like homogeneous in nature. That means we can say a solution is a homogeneous mixture of two or more components. Homogeneous mixture of two or more components is generally called as a solution. So in this particular example, here we have mixed the first component as sugar and the second component as water. That means this mixture will form homogeneous mixture. Okay, and apart from that, if you take another example, take sodium chloride, which is a table salt, sodium chloride. Add this sodium chloride to water. So before we add the table salt or sodium chloride to water, we can identify the particles of the sodium chloride. But the moment we add NaCl to water and mix thoroughly, we cannot identify the NaCl particles or sodium chloride particles in the resultant mixture. That means this too also generally forms the homogeneous mixture. That means we can say the aqueous solution of sodium chloride is also a particular homogeneous mixture. So we can say this is also a solution. So basically solution is the homogeneous mixture of two or more components. So both the examples I have taken only two components. So first one is water, both the cases is common, and the other is, in the first case we have sugar, second case we have sodium chloride. Take a third example. Suppose I am taking again sugar and salt and water. Now here we have three components. So add these two to water. This mixture also generally forms a homogeneous mixture. So automatically we can also call this as a solution. In the first two cases, we are saying only there are two components. First one and second case, we have only two components, where the solution having only two components is basically called as a binary solution. Binary solution. So what is a binary solution? Means the solution or a homogeneous mixture of only two components is basically called as a binary solution. If it is three components, it is called as ternary. If it is four, quaternary. So usually we'll come across about the binary solutions mostly. That means there will be two components. So in the first case, the one component is sugar, the other is water. And definitely we see, if you compare these compositions, okay, here water will present in large excess or more in proportion in the resultant homogeneous mixture, and sugar is present in smaller proportion. In the second case, water is present in larger proportion and salt is present in smaller proportion. In the third case, water is present in excess or larger proportion, the remaining two components are present in smaller proportion. That means based on this, the components which are present in the resultant solution, we can classify or we can divide them into two categories or two types. Okay, the one which is present in a larger proportion is generally called as a solvent. So in the binary solution, so as I told you here, first one is sugar, in the first example, the second one is water. So sugar is present in small proportion. Water is present in larger proportion. Larger quantity is water and smaller quantity is sugar. Okay, and in this case, the one which is present in smaller proportion is generally called as solute. And here this is generally called as solvent. That means in the binary solution, we can say it is a homogeneous mixture of solute and solvent. Is a binary solution. Is a binary solution. So in the binary solution, always the solute is present in smaller proportion, the solvent is present in larger proportion. Suppose if I take for example the aqueous solution of alcohol, suppose you take here alcohol and water. So assume here we have only 10 ml of alcohol, about 90 ml of water. So in this case, alcohol present in smaller proportion, so it must be a solute. Water is present in larger proportion, so it must be a solvent. Or if I take a reverse, suppose alcohol plus water. So in this case, I am taking alcohol as 90 ml, water as only 10 ml. That means in the first case, alcohol is solute, water is solvent. In the second case, alcohol present in larger proportion, so alcohol must be a solvent, and water must present in smaller proportion, so water is a solute. So likewise, based on the proportionation of the corresponding components, we can say or we can decide which is solute and which is a solvent in the resultant solution, or in this particular case it is a binary solution. Binary solution. Okay, and apart from this, suppose if I take the combination of various examples, I have taken here sugar and water, or I have taken the alcohol and water, or else take the mixture of carbon dioxide and water. In all these three cases, if you check once what is the resultant solution physical state, in the first case it is a liquid, second case it is also a liquid, third case is also a liquid. From this, what we can conclude here, by the addition of a solid to a liquid component, in this case this is a solute, this is a solvent, resultant solution is a liquid. In the second case, alcohol is a liquid, water is a liquid, the resultant solution is a liquid. And third case, CO2, carbon dioxide, is a gas, water is a liquid, resultant solution is a liquid. That means in these three cases, solvent is a liquid. So the resultant homogeneous mixture is also a liquid. So from this we can conclude that the physical state of a solution is decided by the physical state of the solvent. Physical state of the solvent here. So in the three cases, water is used as a solvent. Solute can be either solid or liquid or gas. So here the resultant solution physical state is decided by the physical state of the solvent only. Suppose you take another example. I am taking the hydrogen gas, which is in contact with the palladium metal, solid. So resultant mixture is again homogeneous, but its physical state is solid physical state. This basically will come across about the hydrogenation of oils, where the oils will have the unsaturation, nothing but double bonded system as well as triple bonded system between the carbons. So they need hydrogen gas. The reaction is hydrogenation, where the oils combines with hydrogen gas. There we usually use the catalyst. The catalyst is palladium. So of course we can call the absorption of the hydrogen gas by the palladium is generally called as occlusion. Occlusion. Of course we learn this in surface chemistry. Anyway, so here this is a gas, this is a solid. Resultant solution is homogeneous, but it is in solid physical state. Similarly, take any alloy. We are aware alloy is the homogeneous mixture of two or more metals. Homogeneous mixture of two or more metals is alloy. Suppose we take nichrome, a nichrome. So it is having the mixture of the nickel, chromium and iron. We are aware all these are actually solids. So this resultant mixture is again a solid physical state. That means in these two cases the solvent is a solid. Overall solvent is a solid. That means the overall resultant mixture or a solution physical state is generally depends on the physical state of the solvent. Physical state of the solvent. Suppose if you take for example, you have an idea about fuming stone. Fuming stone. So where it is a solid stone, it is having certain gaps in between them. So the gaps are occupied by the air or some other gases. So here solid is a rock or the stone here, and the solvent is in the form of the solid only, but coming to the solute it is a gas. But resultant mixture is actually it is a solid. So here the second case, in every case we can see example 4, 5 and 6 one is fuming stone. In all these cases the solvent is solid. Okay, and apart from this, if you take an example, another example here, that is air. So we are aware the air is having the major components as nitrogen as well as oxygen. These two are major. The remaining gas are trace elements. So here the nitrogen percentage is more. That means we can say in the air the nitrogen can act as a solvent. Oxygen is a solute. So as per the discussion, since the nitrogen is having the physical state of the gaseous state, that's why here air is also a homogeneous mixture of two or more gases. Nothing but it is also a solution only. It is also a solution only. But here we can say if you take the rest of the other gases are negligible or neglected, so definitely air is the homogeneous mixture of nitrogen and oxygen. Nitrogen present in larger proportion, so it is a solvent. Oxygen present in smaller proportion, it is a solute. So resultant mixture is now present in the gaseous state. It is a gas. Or take another example of air in the combination of water. So are we aware water vapor is present in the air. So what is small droplets here? So those small droplets, when they are incorporated, present in the resultant solution, since air is a gas, okay, and water droplets are liquids here, but resultant combination is a homogeneous mixture. It is present in a gaseous state. So here also we can say the resultant mixture is physical state is depending on the physical state of the solvent only. Solvent only. This is how we can understand the classification of the solutions based on the physical state. So solutions can be solid, solutions can be liquid, solutions can be gases. That is purely depending on the physical state of the corresponding solvent. Will decide the physical state of the resultant solution. And apart from this, suppose here we can also classify the solutions into different kinds, like saturated solution, unsaturated solution, supersaturated solution. So in coming the first case here, what we meant to say, what is a saturated solution? Here at the given temperature, assume we have certain quantity of the solvent. If the solvent is able to dissolve certain amount of the solute, and beyond that, if you add even though large quantity of the solute, it won't get dissolved. Just for example, assume we have 100 ml of the water. To this 100 ml, assume at the given temperature only 1 gram of sugar can be dissolved. Even if you add 1.1 grams also, it won't dissolve. Only 1 gram is exactly can dissolve in the given quantity of the water as per this example. So assume 1 gram of the sugar is exactly soluble in 100 ml of the water at the given temperature. Then we can say the resultant solution is a saturated solution. That means at the given temperature conditions, the required quantity of the solute is present in the resultant solution or the solvent. Then we can call the resultant solution as the saturated solution. And here if you add 1.1 grams of the sugar, the remaining 0.1 grams, it won't undergo any dissolution at the given temperature. So that kind of solution we call it as a saturated solution. Okay, and coming to unsaturated, and assume the same 100 ml of water we have added 0.9 grams of sugar. Exactly it requires 1 gram, but we are adding only 0.9 grams of sugar. So this kind of solutions means where the amount of the solute which is required we haven't added at the given temperature. So we have added only the amount which is less than required. In such a case, we can call the solution as unsaturated solution. Unsaturated solution. Okay, and coming to the third case, supersaturated solution. Suppose if we add 1.1 grams of the sugar to the 100 ml of the water just by raising the temperature. So initially this can have the ability to dissolve only 1 gram of the sugar at the given temperature. But we are adding 1.1 grams of the sugar which is more than required. We are adding more than required amount of the sugar. So the resultant solution we can call it as a supersaturated solution. So generally, in order to increase the solubility, we have to raise the temperature. That means we can say here the dissolution of a solute in the most of the cases it is endothermic process. Means we are supplying some heat in the form of the temperature, rise in temperature. So with rise in temperature, the solubility generally increases in most of the cases. That's why there is a relation between the solubility and temperature. So from that we can say with the rise in temperature, solubility generally increases. With few exceptions. If you take a gas here, so solubility of a gas generally we can say it is exothermic. That's why if you take aquatic plants, they are survivable only at the lower temperature. If you raise the temperature, what happens is the dissolved oxygen which is present in the water will undergoes, of course initially at lower temperature dissolved, but undergo undissolved. That's why it becomes difficult for the aquatic plants or the animals to survive at higher temperatures because the dissolved oxygen value will decrease. These kind of we have some exceptions here, but in general, apart from these exceptions, in general, so the dissolution is a endothermic. That's why with increase in temperature, solubility generally increases. This is how we can classify the again solutions into saturated, unsaturated, and also supersaturated solutions. Yeah, and every time we are saying we are dissolving certain quantity of the solute in the resultant solvent to form homogeneous mixture. Now, in order to understand how much of the solute which is present in the resultant solvent or solution, we generally call it as methods of expressing strength or concentration. So let us see the various concentration terms in this particular chapter, that is concentration. This generally shows how much of the solute is present in the resultant solution of the solvent. In every time we have seen certain quantity of the solute we are dissolving in suitable amount of the solvent which is able to form a resultant solution. That we call it as a strength or the concentration. So simply we can say the amount or the quantity of the solute that is present in the given quantity of the solvent or solution, we call it as a concentration. We have different methods to express this particular concentration. Let us see the first one as weight percent. Can also use a W by W percent. Nothing but weight of the solute present in 100 grams of the solution is called as weight percent. It is the weight of the solute present in 100 grams of the solution is generally called as weight percent. It is also one of the concentration term. So as per definition, we can write this as weight of solute in grams by weight of solution in grams into 100. For example, if I say 100 or 10% weight by weight sodium chloride, NaCl. So from this we can understand that 10 grams of the NaCl present in 100 grams of the resultant solution. So from this, what is the weight of the sodium chloride, NaCl? 10 grams. What is the weight of the solution? 100 grams. That means here 10 grams of the NaCl is present in 100 grams of the solution. That's why we are calling the solution as 10% weight by weight NaCl. This particular thing we call it as weight fraction. So always weight fraction into 100 will give weight percent. So this is called as what? Actually weight fraction. This weight fraction into 100 will give the percentage of the weight. So this is nothing but weight percent. So simply it is the weight of the solute in grams present in 100 grams of the solution. It's called as weight percent or weight by weight percent. Weight by weight percent. And coming to the second one, weight by volume percent. So here also the weight of the solute in grams present in 100 ml of the solution. Weight of the solute present in 100 ml of the solution is called as weight by volume percent. Weight by volume percent. So as per definition, so weight of solute in grams divided by volume of solution into 100 ml. So this is weight of the solute in grams present in 100 ml of the solution. So we can call this weight by volume fraction, W by V into 100. This we can call it as weight by volume fraction. So we are calling this as weight by weight fraction. We are calling this as weight by volume fraction. This into 100 will give the weight by volume percent. Okay, for example, here also, suppose if I take 1% weight by volume sugar or salt, whatever it may be. So in this means we have 100 ml of the solution. In this 100 ml of solution, 1 gram of the sugar is present. 1 gram of the sugar present, then only we can call it as 1% weight by volume. 1% weight by volume. This is how we can define the what is weight by volume percent. Weight by volume percent.
If you like this video, please give a thumbs up. Please subscribe to our channel to get more videos on CBSE syllabus.